Hello, everyone. Today we have Chi from Virginia Tech who will be talking about graphs with many Hamiltonian paths. Before we begin, let's recall our three guidelines. We are all learning, no one has all the answers, and everyone has something to contribute. And with that, Chi, take it away.
All right, thank you, Aditya, for introducing me. Hi, I'm Nguyen, and I will be talking about graphless many Hamiltonian paths today. This was a research that I did during my senior year as an undergrad. So, with Dr. Murphy Kate Monty at Carleton College. So, I'm excited to show you like what we've done and possibly the next steps forward. From this research. So, true to form, we'll be talking about graph with many Hamiltonian paths, including the two extreme that I'll introduce next. So we'll start with some preliminary definitions for the people who might not be familiar with graph terminology, and then transitioning into the two extremes that I talked about, nearly Hamiltonian connected non-Hamiltonian graphs, and then I'll be talking about a construction for minimal Hamiltonian connected graph. So if you don't know what those words mean, we'll get started on learning what they are. So first of all, to introduce some definitions, a Hamiltonian path in a graph is a path which visits every vertex exactly once. And a graph is Hamiltonian if it admits a Hamiltonian cycle. So a Hamiltonian cycle is a Hamiltonian path that has the same beginning and ending vertex. Um, and a graph is called homogeneously traceable if every vertex of the graph is a starting vertex of a Hamiltonian path. And then this is the star of this like whole research, right? So a graph is Hamiltonian connected if every pair of vertices in the graph is connected with a Hamiltonian pair. A Hamiltonian path. So this basically means that if I give you a graph and then or you give me a graph and then like a Hamiltonian connected graph, and I can choose like two random vertices, and I'm guaranteed to find a Hamiltonian path connecting them. So there's just any random pair of vertices gives me a Hamiltonian path. That this means that this graph is going to be Hamiltonian connected. So there's an implication here that every Hamiltonian connected graph must be Hamiltonian. Obviously, right? You just like have if you choose a pair of vertices that are going to be adjacent, which means that they're joined by an edge, there is going to be a Hamiltonian path between them, thus a Hamiltonian cycle. And then so every Hamiltonian graph must be homogeneously traceable. So let's take a look at just like some more definition that we'll be introducing. The question that motivates half of this research is basically just asking how many Hamiltonian paths can a non-Hamiltonian graph contain? So is it possible to pack just as many Hamiltonian paths as possible into a graph before like without making it Hamiltonian? So we will be considering graphs with many Hamiltonian paths in this case through the following definition. So we call a graph G k-pair strung if k pairs of vertices in G have a Hamiltonian path between them. So Hamiltonian connected graphs are going to be n choose 2 pairs strung because they have n choose 2 pair of vertices. Thus, it's going to be n choose 2 pairs strung. And because there are graphs that are homogeneously traceable, but also non-Hamiltonians, or you can abbreviate it as HT and H, this implies the existence of non-Hamiltonian graphs that are at least n divided by 2 pairs strung. And you can see an example over here, the Peterson graph. So the Peterson graph is, for any one of you who knows graph theory, you know that the Peterson graph is a very infamous like counterexample to a lot of properties, right? So the Peterson graph is, as you probably already know, it's non-Hamiltonian, which means that it does not contain any Hamiltonian cycle, but it does contain a lot of Hamiltonian paths, and specifically, there are 30 different 30 different Hamiltonian paths in this Pearson graph. It is 30 pair strung. meaning that there are 30 different pairs of vertices that are connected by a Hamiltonian path. And how do we find this? Well, it's pretty simple, because in this case, for the Peterson graph, it's very symmetric over here. And then if you want to find or do a raw calculation of how many Hamiltonian paths that is contained in the Peterson graph, you can just see that you can have any you can have a Hamiltonian path between any two vertices that are non-adjacent. So for example, if I take um, this vertex over here and then this vertex, so you can see that there is no edge joining these two vertices, and there is a Hamiltonian path connecting these two vertices. So taking any two pairs of vertices in the Peterson graph that are non-adjacent, which there are 30 pairs, you will have a Hamiltonian path. Thus, the Peterson graph is 30 pairs strong. Now, to talk about exactly, to quantify the let's say the ability of non-Hamiltonian path to to contain as many non-Hamiltonian graph to contain as many Hamiltonian paths as possible, we talk about the pair connected ratio of a graph. So what is that? So let G be a graph of order n, and then we can define the pair connected ratio of G to be R sub G equals to the max of this K divided by n choose 2. So n choose 2 is the number of pair of vertices in G, right? So this is just taking the number of pair of vertices that are joined by a Hamiltonian path and divided by the number of pair of vertices in general of the graph. So R sub G is equal to max of K divided by n choose 2, where G is K pair strong. So there's the pair connected ratio of G. And we can bring this definition further to just family of non-Hamiltonian graph of a specific order n. For example, so if n is any natural number, and we let R sub n be the supremum of all these R sub G, where G is a non-Hamiltonian graph of order n. So it has n vertices. And then we define big R to be the supremum of all of this R sub n, where n is greater than or equals to 3. We can establish an upper bound on R sub n and an upper bound for R. And in fact, we can derive a specific value for R. And so this kind of informs us of just how basically if there are families of graphs that are non-Hamiltonian but can have as many Hamiltonian paths as possible, basically almost all pairs of vertices in the graph can have a Hamiltonian path connecting them. So this is what we want to study through these pair connected ratio. So we can establish an upper bound on R sub n. Specifically for any n greater than 3, then we can have that R sub n is going to be smaller than or equals to n minus 2 divided by n. And then the discussion of the proof goes as follows. If the graph G has only one Hamiltonian path, then obviously there is only going to be two vertices. There are going to be two vertices that are joined by a Hamiltonian path, right? So it's going to be 2 to R sub G, it's going to be 2 divided by n, 2 divided by n times n minus 1. So this is 1 divided by n choose 2, right? Which gives you 2 divided by n times n minus 1, which is definitely smaller than n minus 2 divided by n. But if graph G has at least one more Hamiltonian path, then K, let's say, not then K, then the number of Hamiltonian pairs, let's say pairs of vertices that are connected by a Hamiltonian path is going to be characterized by the number of non-adjacent vertex pair. So it's just going to be R sub G equals to n minus 1 times n minus 2 divided by 2, and then all divided by n choose 2. And then you can verify that this is also smaller than or equals to n minus 2 divided by n. So we establish an upper bound on R sub n. What about an upper bound on R? So from the definition, well, it's a pair connected ratio, right? You can't really go any further than a non-Hamiltonian graph is going to have max n choose 2, not even n choose 2, just max n choose 2 pair pairs of vertices that are going to be joined by a Hamiltonian path. So it's pretty obvious that from the definition that R is going to be smaller than or equals to 1. But in fact, we can show that R is going to be equals to 1. And then we can also, we conjecture for now that for every rational number q between 0 and 1, not including 1 and including 0, there is going to be some graph G that has a pair-connected ratio R sub G equals to Q. So here, for example, Q, if Q is equal to 0, then obviously it does not have any Hamiltonian path, right? So that's nice. We can conjecture this and we can have the theorem that R is equal to 1 and we can show it. And then, so to show that R is equal to 1, we are going to rely on a very constructive proof, and specifically by describing a construction that produce a family of graph which are with R sub G approaching n minus 1 for any natural number n. So we introduce the following definition. A set of edges. So here we're going to define everything through edges now. So sorry, a set of edges S equal to E sub 1 all the way to E sub n. So n edges in the set. In a graph, G is each path connected if for every I not equals to G. There is a Hamiltonian path with this endpoint in E sub I and E sub J, containing every edge in S, with the exception of E sub I and E sub J. So to look at a concrete example that's easier to know what exactly I'm talking about, so we can take a look at the smallest known almost hypohamiltonian graph. So hypohamiltonian graphs are just graphs that are basically one vertex away from being Hamiltonian. So this graph, if it's not really easy to see, I can zoom in right here. So there's a graph over here. There is a central vertex right here that makes it non-Hamiltonian. So if I eliminate this central vertex over here, I'll get a Hamiltonian graph. This is why it's called a hypo-Hamiltonian graph, right? So the smallest known almost hypo-Hamiltonian graph. And this is a graph with an H path connected set, edge set of size 7. So there are 7 different edges here in this edge set. So this is edge 1. So this is E1, E2, E3, E4, E5, E6, and E7. So we have 7 different edges here, and this forms an H path connected set. And then you can see here the Hamiltonian path connected. Each pair of edge are going to be shown in green. Yeah, so you can see it for yourself here. So this is what a graph with an H path connected set kind of looks like. This is of size 7, 7 different edges, right? And what exactly are we going to do with this? Well, we're going to be constructing a family of highly pair-strung non-Hamiltonian graph. So if we let G be a non-Hamiltonian graph and let K be an n, a natural number, and obviously we have to make sure that this G graph has to contain my H path connected set, right? So let S be E1, E2 all the way to En. There's going to be my set of H path connected edges, and we can label each endpoint of the each edge. So let's say I have E sub I over here. So this might be, so let's say this is my E sub I, for example. And so we can label each of the endpoint of each of these edges, E sub I with V sub I and W sub I. And then, so we construct G sub K as follow. To each, so this is, let's say this is my graph G, right? And then I'm going to construct G sub K by to each edge E sub I. We're going to attach a complete graph with K vertices. So for example, if I want to construct G sub 3, then I can construct K3. So this is a complete graph with 3, let's say K4 instead, so it looks easier. So I can have K4, it's going to look like this. It's a complete graph, right? So I have my complete graph K4 over here. This is my Ki. K2 to the I. This is a 4 complete graph. And then we're going to attach every vertex of ki to v sub I and w sub I. This is how we're going to be constructing my G4 graph. So I'm going to be connecting. So what does it mean to connect or to label k sub I such that every vertex of k sub I is adjacent to v sub I and j sub I is going to look like this. To each of these vertex, I'm just going to connect it to v sub I and w sub I. So it's going to look something like this. Maybe this. There we go. And then over here as well. So basically, every of these vertices is going to be connected to my 2 end vertices of the edge. So it looks something like this. Look a little bit messy. And I'm going to do this to every single edge that is in my H-path connected set or H-path set. Does that make sense? And so just doing this process, just going through all of the edges in my H-path connected edge set and just attaching all these complete graph with k vertices to all of these edges is going to give me my G sub k graph. And then I am going to claim that the pair connected ratio of this graph is going to be approaching n minus 1 divided by n. And how do I prove that? First of all, I have some properties of the graph G sub k. So we started out with G be a non-Hamiltonian graph. So the first lemma is going to be for each k in n, for each k a natural number, and G sub k is going to be non-Hamiltonian. And then second of all, there is however, going to be a Hamiltonian path from each vertex in case I, so each vertex in my complete graph over here to each vertex in my kj. So there's say there's like a different edge over here, which is E sub j over here, and I'm just going to be connected kj to this. And then so the second lemma say that if I start with any vertex in this complete graph, I'm just going and want to go to like a vertex to in the other like complete graph, there is going to be a Hamiltonian path connecting them basically. And then the theorem, the big theorem is going to be if G contain any a set of n greater than 1 edges, which is H path connected, then R sub G sub k. So this the pair connected ratio of my graph G sub k that I just constructed is going to be approaching n minus 1 divided by n. So we're going to be showing the proof of the theorem, not the proof of the lemma. You can ask about it at a different time, but so to prove the theorem, we are going to introduce another theorem, which is so let G be equals to the complete or let G be the complete bipartite graph k sub n plus 1 with bipartition vertices at a1 all the way to an and then b1 all the way to bn plus 1. So then the set S equals to A1, B1 all the way to AN, BN is going to be an H path connected set in G. So if you don't know what a complete bipartite graph is, basically let's say we have a K3, 4. It's going to look something like this. This is going to be my A vertex set, and then this is going to be my B vertex set, for example. And then I'm just going to have edges connecting all of them like this, right? Blah, blah. And then, yeah, you get the idea. I'm not going to draw out all of them, but then I'm guaranteed that by this construction, or like I'm guaranteed that with this complete bipartite graph, I'm going to have an H-path connected set. So this theorem allows me to find H-path connected set in any of the non-Hamiltonian graph G that I started out with. So to prove this, we are going to show that there is a Hamiltonian path connecting each pair of edges in S. Which is the set that we want to show that is H-path connected. So the path bi, ai, b I minus 1, ai minus 1, all the way to b1, a1, bn plus 1, an, bn, an minus 1, bn minus 1, all the way to aj plus 1, bj plus 1, ai plus 1, bi plus 1, all the way to aj, bj is Hamiltonian, contains all the edges in S. Might not be obvious right now or in this, but if you just work with over any example and you follow this construction, you should get a Hamiltonian path that contains all the edges in S. And so this kind of gives us a guarantee that for any graph G, non-Hamiltonian, that we started out with, we're going to get some sort of like edge path connected, edge set, right? So this is good because then we can actually finally prove the maybe did I have it here? No, I did not have it here. That's fine. We maybe not, but I'll prove that in the interest of time. Yeah, I only have 30 minutes left, so maybe not prove that. But we're gonna have with this construction, we are going to have this, that if G contains the a set of n greater than one edges which is H path connected. So this is what we have from the theorem earlier, right? We're gonna have that R sub G sub K is going to approach n minus 1 divided by n. And then we have the theorem there that is going to give us the construction or like the H path connected set. And so from this, we're going to have the corollary that there is going to be a family of graph G sub K such that R sub G sub K approaches n minus 1 divided by n as n approaches infinity. And then thus n is going to be equals to 1. I did not include the proof of the theorem here. Completely forgot about that, but you can feel free to ask me afterwards. So that concludes the portion where we talk about graph with with many Hamiltonian paths. So you see here this ratio, or like this R equals to 1 here, implies that we can construct an infinite family of graph that is going to be non-Hamiltonian, but pack as many Hamiltonian paths as possible before becoming Hamiltonian, right? So we don't want it to become Hamiltonian, but we want it to have as many Hamiltonian paths as possible. So what about the other extreme? So this kind of motivates the second part of our research, which is just looking at graphs that are Hamiltonian connected, but as few edges as possible. So that's so basically we want to construct an infinite family of graph that has that is Hamiltonian connected, but has as few edges as possible as allowed before it loses the Hamiltonian connectedness, right? So in order to do that, we're going to be using a result established by Nguyen in his paper on a problem of OR, I think in 1965, which states that if G is Hamiltonian connected with n greater than 3 vertices, then every vertex is going to have a degree of at least 3, and then G must have at least 3n divided by 2 edges. So obviously, if I can construct a family of Hamiltonian connected graph that has 3n divided by 2 edges, then I'm guaranteed that that family that I just constructed is going to be minimal edge, right? So this is the lower bound on the number of edge. If I can achieve this lower bound, then I'm guaranteed that my family of Hamiltonian connected path is definitely going to be minimal. And then how am I going to do that? Well, I'm going to be constructing a family of graph of even order. So I'm just going to be looking at even order and a specific type of even order first. We construct a family of graph of even order m is equal to 2n, which has 3n edges. So you can see here that this definitely guarantees us that the number of edges is going to be just like 3n. So this achieves the lower bound that Nguyen set out in his paper, right? So if so we are guaranteed that this is like minimal edge, and that if I can show that this family of graph is definitely going to be Hamiltonian connected, then I am guaranteed that my construction is going to give me a family of minimal Hamiltonian connected graph. So we construct a family of graph of even order 2n, which is going to have 3n edges, and then we're going to show that these graphs are going to be Hamiltonian connected. So this is my proof, or this is my construction. So we are going to start our construction with C sub 2n, where n is equivalent to 0 mod 3. So let's say I'm going to start with n is equal to 3. This is the lowest case that I can go. So I'm going to be looking at the C6 graph. And it's going to look something like this. A little bit of a tight squeeze in the space right here. But this is my C6 graph. And then I'm going to label the vertices of C6 in this case, or C2N. In general, we're going to label it as just 0, 1, 2, 3, 4, 5 in this order. So it can go all the way up to 2n-1, right? Depending on what n you're choosing. So we have this. So obviously here 2n-1 is equal to 5. And then now I have this cycle graph, C6, but then I want to construct my like graph that has 3n edges, so I have to add edges to this. So I'm going to add the edge 0n, which is going to be 0, 3 in this case, 1 n plus 2, which is going to be 1 5. So n plus 2 is equal to 5 in this case. I'm going to connect 1 with 5, and then 2 with n plus 1, which is 4 in this case. So 2 and 4 is going to have an edge between them. And then obviously, if you have more vertices, then you can go on and on, right? 3 is going to be connected to n plus 3. 4 is going to be connected to or have an edge with n plus 5, and 5 has an edge with n plus 4. So it's kind of like alternating, basically, until every vertex has degree 3. So in this case, in the case of C6 over here that we just looked at, it's already have degree 3 for each vertex, so we don't have to worry about adding more edges. So this specific case, but more precisely in general, for any n equivalent to 0 mod 3, we can define gamma sub n to be the graph with vertex set v of gamma sub n equals to 2n, and the edge set E of gamma sub n. So here, this is my C6 graph with additional edges. So this is going to be the gamma sub 3 graph over here. So it has 3n, which is 3 times 2, which is 6 vertices, right? And then edge set of E of gamma sub n is going to be all the edge of this cycle graph C sub 2n, and then union with 3i, the edges between 3i and 3i plus n, and the edges between 3i plus 1 and 3i plus n plus 2, and the edges between 3i plus 2 and 3i plus n plus 1, where I ranges from 0 to n minus 1. So this is going to be the general construction of my gamma sub n graph with n vertices and 3n edges. So this guarantee to give me 3n edges, and every vertex is going to have a degree 3. And so I can construct the graph of gamma sub 3. In fact, I just did. I just constructed the graph of gamma sub 3, but I can also construct the graph of gamma sub 6 and gamma sub 9 using these steps. So over here is a general over here is a figure, or like a drawing, I don't know, of the graph of gamma sub 3 is over here, and gamma sub 6, you can see that we start with a C12 graph over here, right? So 12 different vertices, and then we just keep adding. And then similarly for gamma sub 9 over here, we start with C sub 18, 18 different vertices, and then start adding edges to give us graphs that have like 3 times n edges. So this construction does give us like graph of like 3n edges if we start out with 2n vertices, right? So this should satisfy, obviously this only if n is equivalent to 0 mod 3. So in other cases, I'll talk about it in a bit later. But this construction, if we can prove that these graphs are going to be Hamiltonian connected, then it's going to be satisfying Moon's like lower bound for the number of edges in a Hamiltonian connected graph. So if we can prove that these graphs are Hamiltonian connected, then we are guaranteed that we're going to have like our family, or our infinite infinite family of graphs that are going to be Hamiltonian connected and minimal, right? So that's the goal here. So we're done with the construction. Now all that's left is just to prove that they are Hamiltonian connected. And I'm going to do that by using a different construction. So obviously we can get any gamma sub 3n or whatever, like gamma sub 3n, 3n, whatever, right? But obviously we can get all that from the cycle graph, which is like c sub 2n, as you can see from the previous construction, or we can construct it with a kind of like inductively by going from a graph of smaller order. So to do that, we can do construction of gamma sub n plus 3 from gamma sub n. So let's go back to our familiar our friend, the gamma sub 3 graph. If you remember, it looks something like this. So start with C6, right? And then just it's a little bit small over here, but 0, 1, 2, 3, 4, 5. And then there are edges from 0 to 3, 1 to 5, and then 2 to 4. So this is my gamma sub 3 graph. And then maybe I want to construct gamma sub 6 from this. So how do I do that? Well, one of the things that we did earlier was that we constructed gamma sub 6 from C12, but now we can construct gamma sub 6 inductively from gamma sub 3. And how do we do that? Well, we're going to add 3 vertices, let's say A, B, C, between the vertices 2 and 3. So in general, if I want to construct gamma sub n plus 3 from gamma sub n, we can add vertices a, b, c between the vertices n minus 1 and n. So n in this case is going to be equals to 3. So let's add 3 vertices a, b, c between n minus 1 and n. So I'm going to add, maybe it's a little bit hard to see. Maybe I can move it over here. It's not much better, but maybe it's like easier to see over here. So I'm going to add ABC here. A, this B, and then this C. Wait, actually, hold on. Here. So A, B, and then C. So this gives us an additional 3 vertices, right? But then we need another 3. So I'm going to add alpha, beta, gamma after the vertex 2n minus 1. So between 2n minus 1 and 0. So this is alpha, beta, gamma. So now we are going to have a total of, for example, in the context of the gamma sub 3 to gamma sub 6 graph, we have a total of 12 vertices around here already. So this kind of matches up with our construction of gamma sub 6 from C12, right? We have 12 vertices, and now we just need to add the edges so that we can get the 3n edges with degree 3 vertices all around that we have earlier. So we're going to be connecting the edges of so we're going to be connecting A with alpha, so here, and then B with beta, and then C with gamma. It's kind of hard to see here. They're not joining at the same place, by the way. It's just because I drew this kind of weirdly. But from this, right, so from this alone, we can see that gamma sub 3, 3 plus n plus 3, gamma sub n plus 3 is going to contain all the edges in gamma sub n, except for n minus 1 and n. So n minus 1 and n no longer exist because now we have 4 different edges in its place. So we're going to have, except for the edge between n minus 1 to n, so no edge between 2 and 3, and n minus 2n minus 1 and 0. So no edge between 2n minus 1 and 0, no edge between 5 and 0, because now we have like edges in between like this, right? So now we're going to have the additional edges A to alpha, B to beta, and C to gamma, and then all the edges in between, like 2 to A, and then like, like A, B, B, C, and then C to N, which is C to 3 in this case, and then 2N minus 1 alpha, so 5 to alpha, and then yeah, like alpha to beta, beta to gamma, and then gamma to 0. So these are the edges that gamma sub n plus 3 have that gamma sub n does not have. So this is really just a different way of constructing the gamma sub n plus 3 graph without relying on the cycle graph earlier. So this is an inductive construction. And just from this construction, you can probably kind of guess what the proof will be, right? So the proof to this theorem that for any n equivalent to 0 mod 3, where gamma sub n is a Hamilton for any n equivalent to 0 mod 3, gamma sub n is a Hamiltonian connected graph of order 2n with 3n edges. So we're going to be using an induction proof on this, but then I'm going to do that by partitioning the vertex sets. So we're going to be partitioning the vertex set of gamma sub n plus 3. So remember, we're talking about the construction from gamma sub n now. So not the construction from C sub 2n plus 6, not that anymore. We're going to be talking about the graph that we get from constructing, by constructing it from the gamma sub n graph. So we're going to be partitioning the vertex set of gamma sub n plus 3 into, first of all, the new vertices, which are just the vertices that we added to my gamma sub n graph, right? So it's A, B, C, alpha, beta, gamma. So if you want to look at what it looks like over here, so it's these six over here, alpha, gamma, beta, and then A, B, C over here, my new vertices. So this is a new vertex set. So we denote it by n. And then the proximal vertices set, which is P. So it's going to be all the, it's proximal, right? So kind of like glean from the name that it's going to be all the vertices that are close to the ones that we just added. So it's going to be 0, n, and then n minus 1, n minus 2, 2n minus 1, 2n minus 2. So in this graph over here, it's the vertices indicated in circle, right? So it's going to be my proximal vertex set. So it's going to be 0, n minus 2, n minus 1, n, and then 2n minus 1, 2n minus 2. Pretty straightforward. And then the rest is just going to be the orbital vertices. So orbital vertices are all the 1, 2, all the way to n minus 3, and then n minus 1 all the way to n minus 3, right? So it's going to be all these vertices over here. These are my orbital vertices. So they are denoted in squares over here. Okay, so what's the point of partitioning the vertex set into this? It's going to be pretty easy now that we have this to prove that, well, if I just pick any two random vertices in this graph in general, I'm going to be guaranteed to have a Hamiltonian path connecting them. So we're going to state a lemma here that suppose that gamma sub n is Hamiltonian connected. So obviously we started with gamma sub n and constructed gamma sub n plus 3. Gamma sub n is Hamiltonian connected is like kind of like the inductive case, right? And then n is greater than or equals to 12. So, well, obviously because we already saw that gamma sub 3, gamma sub 6, gamma sub 9, they are all already Hamiltonian connected. So those are our base cases. So for any distinct vertices, U, V, and O, so these are the orbital vertices, there's going to exist a Hamiltonian path in gamma sub n plus 3 from U to V. So this lemma is going to deal with all the cases where U, V are in the orbital vertices set. So all the ones over here we're done with, right? So just choosing any two vertices from these orbital vertices is going to give us a Hamiltonian path. And so we can rely on that to prove the rest of the cases. So once again, to restate the theorem, if we have any n equivalent to 0 mod 3, then gamma sub n is a Hamiltonian connected graph of order 2n with 3n edges. So suppose that gamma sub n is connected. We want to show that gamma sub n plus 3 is Hamiltonian connected. So let UV be a pair of distinct vertices in gamma sub n plus 3. We will prove that there is a Hamiltonian path connecting them by considering several cases. So case 1 is going to be UV in the orbital vertex set. So we already have the previous lemma that said that if I have any two distinct vertices in the orbital vertex set, I'm just going to have a Hamiltonian path. So that case 1 done. Case 2 is that if U and V is any of the new or proximal vertices, right? So it's in, I should have added the graph over there. It's in one of these over here. So if UV is any of the vertices um, in like these 12 vertices over here, then what do? Well, I can rotate gamma sub n plus 3 clockwise along the cycle C sub 2n plus 6. So the cycle C sub 2n plus 6 is kind of like the base graph that you started out with to construct gamma sub n plus 3 in the first construction, right? So if I rotate this whole thing by 6 vertices, then this is, first of all, this is going to be an automorphism of gamma sub n plus 3. It's just a clockwise rotation, so it's fine. But then this is going to make sure that all of our UV that are previously either new or proximal, this is going to make sure that our UV now is going to be shifted into the orbital set. So UV is going to be in O now, so this is case 1, right? So by case 1, I already have a Hamiltonian path, we're good. So we can do this because the construction is very symmetric. So just doing like a clockwise rotation or counterclockwise rotation is not going to lose us any of the just like Hamiltonian or like Hamiltonicity and stuff like that, right? So this is fine. The construction is highly symmetric, so rotation is just an automorphism. We're fine. So that's case 2. We boil down to case 1. Case 3 is going to follow very similarly, right? So if we have U is in O and V is in N, obviously this without loss of generality. So N here is the new vertices. So we can have that if V is alpha and A. So if V belongs to alpha A, so it can be this vertex or this vertex, then we're going to be rotating our graph just counterclockwise by 3 vertices. So then if we rotate it counterclockwise by 3 vertices, then we're guaranteed, so let's say over here, right, 3 vertices, 1, 2, 3. And then over here as well, 1, 2, 3. Then we already shifted V into the orbital set, right? And then U is already in the orbital set. And so we are probably guaranteed to have that U is still going to be in orbital set, obviously, because we have N is like very large. So in this case, N is greater than 12 or equals to 12. Then we are going to have enough vertices in O such that if we shifted U by 3 vertices counterclockwise, we're still going to land in the orbital vertex set. So U here is still in O, but then V now is going to be in, so V now is going to be in O. And if we don't have enough vertices, then we can shift it, probably going to be in NCB0 beta gamma, which is going to be by proximal or like new vertices, right? So if U is in O, and then we also have a V is in O, then this is case 1. And then otherwise, if we don't have enough vertices and accidentally land outside of O when we're trying to shift U. So this is the second case over here. Then we can just rotate it further 6 vertices clockwise. So this, once again, this is going to shift U back into O, and then it's still going to make sure that V is still in O. So this is going to be case 1 again. So case 3 just boils it down to case 1. And case 1 said that we're definitely going to have a Hamiltonian path connecting these 2 vertices. So really case 3 and case 2 is just going to rely on automorphism on gamma sub n plus 3 in order to get case 1 back. In case 1, we already know that they have a Hamiltonian path connecting them. So for any type of UV in O or UV in N union P or U in O and V in N, we're going to have a Hamiltonian path. So the last case to consider is just U and O and then U and P. So we now can just rotate gamma sub n plus 3 so that v is going to be in n. So this is not going to send u outside of O in this case, because, well, if v is in P, it's just going to be one of these, right? And then if we rotate it so that it lands into the new vertex set, this is like what a one vertex or two vertices at most rotation, or like counterclockwise or clockwise depending on where you're at. So it's not going to land as it's not going to land u outside of O. So we're going to have now that v is in n and then u is in O. This is case 2, case 3. This is going to be case 3 or case 2 if we accidentally land it outside of like u when we sorry, if we accidentally land u outside of O, for example, into P, for example, then we're going to have case 2 and case 3, that we're going to have a Hamiltonian path between U and V. So really, it's all about just like using automorphism on gamma sub n plus 3 in order to get case, in order to just like boil it all down to case 1. So this whole proof kind of like hinges on this lemma that established case 1, right? So we've shown that um, this construction does give us, first of all, a Hamiltonian connected graph, and it's going to be of order 2n with 3n edges. So this guarantee that this achieves the lower bound on the number of edges that is established by Moon in his paper in 1965. So we have constructed an infinite family of graph that is Hamiltonian connected and is minimal. However, this is only for case of n equivalent to 0.3. So we can work the cases of arbitrary even order. So with the assumption that n is equivalent to 0.3, if we want to produce graph of order 2n minus 1, we can just do the graph of order 2n like we just did earlier, and then we can delete the edge beta b and then merge the two edges that share the degree 2 vertices. And then if we want to produce the graph of order 2 times n minus 2, just delete the other edge, so gamma c, and merge the two edges that share the degree 2 vertices. So it all just going to start with the graph of order 2n, and then we just start deleting edges, right? So we believe that these are all going to be Hamiltonian connected, and similar case analysis approach will probably provide a proof of this. The Hamiltonicity of these graphs for at least n small n equals to 84 has been verified by adapting a program that one of our collaborator created, just this Hamiltonicity checker, which has methods for determining the existence of Hamiltonian path between two specified vertices. So at the very least, for n smaller than or equals to 84, this approach works. So beyond that, computer is kind of like not strong enough to handle beyond that as of now. But we don't really have any reason to believe that it does not work. So, and that's the end of my presentation. These are all my references. Thank you for listening. If you have any question, I'm happy to answer.
Thank you so much, G, for the talk. Questions? So you're building graphs for n congruent to 0 mod 3, right?
Yes. Yes, that's the construction in this I'm like suddenly losing word. Sorry, yeah, in this yes, in this paper.
So how do you fill in the rest?
What do you mean for filling the rest?
So like between, you can only show for like 3 and 6, right? How do you show for the stuff in the middle?
Oh, so in the middle, we can take care of that by for this here. So there's like just any even order. For odd order, it's going to be a little bit more difficult. So we haven't done that yet for even order, but this kind of should take care of all the odd. Sorry, we haven't done that for odd order. This should take care of the cases for even order.
Right.
Yes, yeah.
So when you say the Hamiltonicity of these graphs is checked for n less than equal to 84, that is all n between
Yeah,
that?
no, just the even one, I believe. So
Okay.
yeah, so just the even one is going to give us this, and the other ones are not checked. So we just check for like all the vertices and just try to make sure that there's a Hamiltonian map between them. Yeah.
More questions. Okay. So is there any questions? Thank you, Chi, for the talk.
Thank you.